This is lesson 8.1, task 2. All right, we're going to look at exponential growth and decay, and we're going to look at transforming those functions. All right, the general form of exponential function is g of x equals a times b raised to the x minus h power plus k. The parameters a, h, and k in the general form indicate how the transform function and its graph differ from the parent function, f of x equals b to the x power, and its graph. The value of k identifies the vertical translation. Remember, that's similar to other things we've done. K is vertical, moves you up or down. The value of h indicates a horizontal translation. H, horizontal, moves you left or right, and you can see negative h in the formula, so it's going to move you opposite h. And then the value of a indicates whether a vertical stretch or compression, where the graph is reflected across the x-axis. So a, again, stretch or compression. If it's negative, it reflects you across the x-axis. All right, so 3 different functions here to look at. So we've got f of x equals 3x. So we're going to use this as our parent function. And you can see g of x equals 2 times 3 to the x power. And then j of x equals 2 times 3 raised to the x minus 1 power plus 4. So this would be your a, this would be your h and k. All right, consider the function shown in the graph, which is the parent function. So f of x would be your parent function. That's your most basic function of this form. And it says compare the y-intercepts of the graph f and g. All right, the y-intercept of g of x is, the y-intercept of g of x is twice f of x, because f of x is 1, g of x is 2. This change indicated in the equations because the coefficient of g of x. All right, so the coefficient here, 2, is what changes this up to 2. All right, so the coefficient here is 1, that's your y-intercept. Coefficient here, 2, changes that to a 2. All right. This change is indicated in the equations because the coefficient of the base in g of x is twice that of f of x. Again, 2 is twice 1. That's why that was. All right, so compare the values of f of 1 and g of 1. All right, so that's saying when x is 1, what is f of x? Okay, so let's look at the graph. When x is 1, f of x, or your y value, is 3. All right, g of 1. All right, when x is 1 for g function, g is the blue line, and it crosses at the same as the purple line at 6. So g of 1 is twice f of 1. All right, let's see if they want me to write that out. So this is 3, this is 6, twice. All right, so instead of 2 times f1, they want you to write twice. All right, compare the steepness of the graphs of f of x and g of x. How does the equation of the function for g of x relate to the difference in steepness between the graphs of f of x and g of x? All right, so it looks like it is twice as steep. This 2 is going to change the steepness, okay? So it's going to be a vertical stretch of 2. All right, so let's see. Notice that the graphs of f of x and g of x have the same horizontal isotope, y equals 0. How does the horizontal isotope of the graph of j of x relate to the horizontal isotope of g of x? All right, so if we go back to the graph, you can see this green line here, y equals 0. That's an isotope for f of x and g of x. This graph got shifted up 4. This plus 4 was a vertical movement up 4. So the vertical isotope now is y equals 4. So j of x is 4 above f and g. All right, so the horizontal isotope of j of x is 4 below. The horizontal isotope is 4 above. It's 4 above. That's correct. The horizontal isotope is 1 unit. That's not correct. Is 1 unit. So it has to be the second answer. All right, the table shows the first and second reference points for the parent exponential function of any base b. What factor explains why these are good reference points? Select all that apply. All right, so they used the y-intercept, which is 0, 1, and then they used 1 and whatever point that was. So for red, it was 1, 3, and here it was 1, 6. So it's just basically saying, why are those good reference points? So let's see what our choices are. Any base raised to the 0 power is 0. That's not true. Any base raised to the 0 power is 1. So that's the second part. Any base raised to the first power is itself. That's true. 2 to the first is 2, 3 to the first is 3, etc. Any base raised to the first power is 1. That is not true. All right, so they're just saying using those first 2 points, they're always going to have the same rules. Anything to the 0 power is going to be 1, and any base raised to the first power will be whatever you started with, whatever the base is. All right, so how can we move our reference points? So 0, 1, that was our y-intercept for our parent function, and we can move that. You can see this is your general function, a times b, raised to the x minus h plus k. So 0, your x, will move to whatever h is. That was your horizontal movement. So h, and then the y value, this 1, is going to be a plus k. So it's going to be your stretch or compression and your vertical movement together. All right, your second reference point, 1b, is going to be 1 plus h. So 1 plus whatever h is. Here it went from 0 just to h, but now you have to add the 1 because you started at 1 here. And then b is going to be a times b plus k. Because again, b is here, so it's still the same here. You just have to put b in the function there. All right, it says explain how you can use the parameters a, h, and k in the general form of the exponential function to write the ordered pairs that are images of the 2 reference points on the parent function. All right, so if you know the reference points, if you know these points on your parent function, and you know how to just plug the numbers in from your general function, then you can find those 2 new points to sketch the graph very quickly and easily. All right, that's all for task 2. If you have any questions, please let me know. Lesson 8.1, transform exponential decay functions. This is task 3. As with other families of functions, it is helpful to use reference points when graphing transformations of exponential functions. The graph below shows 2 key reference points and the isotope for the parent function f of x equals b to the x and the corresponding information of the transformed function g of x equals ab raised to the x minus h power plus k. All right, so this is going to be useful information. It gives you like the reference points, and it tells you how to find those on your transformed function. So for your parent functions, your first reference point would be 0, 1. And then your reference point for the transformed function is going to be h. Remember, h moves you horizontally, and x is your horizontal movement. So your x is going to move to h. And then your vertical movement is going to be changed by a and k. So you're going to do a plus k to get your new reference point here. All right, your second reference point for your parent exponential decay function is going to be -1 and then 1 over b. So 1 over whatever your b is. And then your transformed reference point will be, again, the horizontal movement comes from h, and you're going to subtract 1 because that's part of the original parent function. And then b will be a over b plus k. So a over b plus k will be the y value of your second reference point. Your isotope will also move depending on what your vertical shift is. So k moves you up or down. So your isotope will be whatever k is. All right, so graph g of x equals 2 times 1/2 raised to the x minus 4 power minus 1. Identify the parent function, the base, and the parameters. All right, so the parent function is the most basic form of the function. So g of x equals 1/2 to the x power is your parent function. The base is 1/2. Remember, if it's between 0 and 1, that indicates a decay. If it's greater than 1, it was a growth. And the parameters are a is 2, h is 4, and k is -1. So those come from your function. What transformations do the parameters represent? All right, so this is going to be a vertical stretch of 2. This is going to be a horizontal shift, right 4. And this is going to move you down 1 unit. All right, find the reference points and the isotope for each function. All right, so the reference points, we're going to use this right here. All right, so we're going to start with 0, 1. And -1 over 1 over b. So we're going to start with 0, 1. This is our parent function. Our second reference point is -1, and then 1 over b. b in this case is 1/2. 1 over 1/2 is just 2. Remember, when it's a fraction, you multiply by the reciprocal. All right, our isotope is just y equals 0. This is the parent function. So a parent exponential function, whether it's growth or decay, is going to have an isotope of 0. All right, now our transformed function. Now our first reference point, if you go back up here, it shows us it goes to h, and then a plus k. All right, so that's what we have to do here. So our h, in this case, is 4. And then we want to do a plus k. So 2 plus -1 is just 1. And then for the second reference point, we're going to do h minus 1 and then a over b plus k. So h minus 1, 4 minus 1 is just going to be 3. And then a over b, 2 over 1/2. So then you end up multiplying that to get 4. Sorry, multiplying by the reciprocal, which is 2. 2 times 2 is 4. And then 4 plus k, the -1, is 3. So that one's 3 as well. All right, and my isotope comes from whatever my k value is. So this would be y equals -1. That means the whole graph is going to be shifted down 1 unit. All right, what is the image on the graph of g of the point 1 and 1/2? All right, if I look at 1, I'm going to go from 1, I'm going to go plus 4, which is 5. So it has to be 5, and then 1/2 we'll have to do let's see, I'm not sure exactly what is the 1/2 going to do. The 1/2 is my horizontal movement, so that's coming from my A, B, and my K. So A, B, and K 2 minus 1 is 1.